Hello everyone, welcome to this class. In this class we will be looking at CVDs, which is chemical vapor deposition techniques, and we will also look at how the SU8 can be used as a mold alternative to silicon. Okay. So, if you remember about soft lithography, right, how we can use PDMS and patent the PDMS using the silicon mold, the similar PDMS can be used when the mold is fabricated using SU8. So, let us understand the advantages also and difficulty also, both things. Okay. So, if you see the screen, if I take a silicon wafer and we want to have a mold which should look like this with a depth of 200 microns. Okay. This is a silicon mold. The silicon wafer thickness is close to 500 microns, assuming we are taking a 4-inch silicon wafer. So, to create this, what we need to do? This is silicon wafer, right? We need to create a oxide layer, thermal oxidation, followed by photolithography, that means we need to spin coat photoresist, the photoresist, load the mask, and the mask pattern should be such that we can create the step, right. So, we have loaded the mask, aligned the mask, you have learned about alignment, right, alignment. Well, the first time the wafer should be in the this way, it should be in the center of the mask like this. And so that the alignment mark on the mask would come on the wafer. Okay. And then there can be a pattern like this, which we are talking about in the cross section, right. So, first time we need to align the primary flat with respect to the mask like this. Okay. There are different ways also, that there are 4 plus. So, you just make in the center of this one, and alignment techniques are also there. So, once you align the mask, next step is the UV exposure, is not it. So, UV light is there, and once you expose the photoresist, right, with UV, of course, you know, do understand, right, whenever we spin coat photoresist, after that what is the next step? Next step is always a soft lithography, soft bake, and soft bake is done at what temperature? 95 degrees centigrade. For how much minute? 1 minute. On a what? Hot plate. It is oven that the temperature remains same, that is 95 degrees centigrade, but the time would vary. Okay, time would vary. So, after this, if I have exposed the positive photoresist with UV light using the mask that I have shown here, what I am expecting? That the unexposed area will be stronger. Good. So, unexposed area is stronger when I develop this particular photoresist after unloading the mask, right, once the UV exposure is done. So, this is what I have. Then I will perform the hard bake, correct, I will perform the hard bake, and then dip this wafer into So, the another thing that I can do before I dip the wafer into the and before performing even hard bake is that I spin coat the photoresist on the back side of the wafer as well. Okay. After the UV exposure is done and photoresist is developed, I will spin coat the photoresist on the back side of the wafer and then I will put this together into the hard bake. You got it what I am saying. So, once you perform this step A, then you have oxidized silicon B, then spin coating and soft bake C, then UV exposure, mask alignment and UV exposure D, then you perform the photoresist developing step which is E, then after photoresist developing step F will be the, after you develop the photoresist you have to etch the silicon dioxide, right. So, for etching silicon dioxide, before that what we will do, we will like I said we will have a hard bake on both the sides. So, the silicon dioxide from the back side is protected when you dip the wafer in BHF. So, when you do that dip the wafer in BHF, then the next step that you get is oxidized silicon wafer. Now, oxide is gone, only it will stay in this area and it will stay in the back side of the wafer as you can see in this particular image, right. So, this is your silicon dioxide and then the photoresist which was hard baked stays intact, photoresist that was hard baked stays intact. So, now what we have? We have silicon that is exposed and because silicon dioxide is etched from the region which is not protected by the photoresist. If we dip this wafer into TMAH or KOH, then silicon, these are the silicon etchants. Okay. So, if we dip this wafer in TMAH or KOH, silicon will get etched, and if silicon gets etched, what we will have? We will have photoresist, oxide, and silicon etched for 200 microns, right. This is what we will have. After this what we will do? We will dip the wafer, we will dip this wafer in acetone. If they dip this wafer in acetone, what we will have? We will have photoresist stripped off from the silicon wafer. Okay. We have photoresist stripped off from the silicon wafer. Now, if I dip this wafer in BHF, buffer hydrofluoric acid, what will I have? I will have my silicon mold, correct. I have my silicon mold. Now, if on this if I spin coat PDMS and cure it, what will I have? I will have, if I cure it and strip this off, strip PDMF off, then I have PDMS which is patterned such that it has a step of 200 microns, because this step that we created in silicon is also 200 micrometers, right. Once I do this, right, my PDMS will be gone from here, because I have created a step in PDMS, as you can see in the schematic. Now, if I again spin coat PDMS onto the silicon wafer, cure it and strip it off, then I will have the same image replicated onto PDMS as long as my mold is intact, as long as my silicon mold is intact. Alright. Now, this is the way that you can create a mold in silicon wafer, but we are looking at alternative, and that is SU8. And what I said, SU8 is it works as a negative photoresist. SU8 works as a negative photoresist. So, for that what we need to do? So, let us see how we can pattern the SU8, alright, how we can pattern the SU8, you will see here. So, you take silicon wafer and you can spin coat SU8, okay, you can spin coat SU8. Let us keep some pattern for SU8, alright. Next is you take a mask, you have to do soft bake after performing soft bake of SU8, and this SU8 is 200 microns. Okay. So, let me draw SU8 a little bit thicker, because if this is 500 microns, silicon is 500 microns, my SU8 is 200 microns, it should look something like this. Now, for SU8 of 200 microns, I will take a mask and mind it, SU8 is a negative photoresist. I will take a mask and expose the area which I want to make strong, and the unexposed area will become weaker. Why? Because SU8 acts as a negative photoresist. So, this is my mask, and now I will do the mask alignment followed by the UV light exposure, right, mask followed by UV light exposure. If I do that, what will I have? I will have a wafer, and of course after this what you need to do? After this you need to first post exposure bake, that means you have to do a hard bake. Post exposure bake, because you have to make sure that soft bake, then exposure, then post exposure bake, then developer. After post exposure bake, the next step is to develop SU8, right. This is a little bit of difference between photoresist and SU8, that after exposure in photoresist you go for developer and then you go for the hard bake, right. In SU8, after exposure you go for post exposure bake, develop SU8, and then you go for the hard bake. Okay. So, after the exposure you go for post exposure bake followed by developer. So, followed by developing means I will have SU8 like this. And then I will perform hard bake, alright. Once I do that, I am ready with my mold. Okay. Now, this is SU8, right. I will spin coat PDMS, cure it and strip off. What will I have? I will have PDMS form like this, isn't it? This one, let us say B, looks similar to. So, if I have PDMS here and I strip it off, cure and strip it off, I will have and this is your A. Does A and B look similar? A and B look similar? Yes, but both are created, one using silicon etching, we call it as micro machining. Okay, because we have etched 200 micron of silicon and then created a mold. In this case, we have performed photolithography and we have created a SU8, created an SU8 step, same 200 microns. So, both ways you can create what we call as a mold. All right. Now, what is the difference between the mold that is created with silicon and mold that is created with SU8? What is the difference, right? The rough, this area, this region, the step is smooth. Okay. This region is also smooth. In case of SU8, it is still a polymer. So, this area, when you perform SEM image, find that it is slightly corrugated like this. It is a polymer. It is a very smooth, but when you zoom in, you will feel that the boundaries are not as smooth as what we get in the silicon. The second thing is that the way the silicon mold is created, this is a standard photolithography technique where you have exposure, you have bulk micro machining and you can create a mold. This is an alternative way where you do not have. So, again silicon, when you do that, right. So, I told you that you can use TMAH or KOH, but alternative technique is go for the DRI, which is called deep reactive ion etching, deep reactive ion etching. Okay. When you do not have DRI with you, see TMAH and KOH are wet etching, right, because there is a chemical involved, while DRI is a dry etching because only gases are involved. Okay. TMAH, tetramethyl ammonium hydroxide, and potassium hydroxide are chemicals, that is why we called when we etch silicon wet etch, while deep reactive ion etching using gas we call it as a dry etch. All right. So, if you do not have access to DRI, but you do have access to photolithography system, then you can go for the SU8 mold. All right, because here you do not have to etch silicon, you do not have to etch silicon. If you have access to DRI, you should go for the silicon mold. Okay. So, that is a difference, that is how the PDMS patterns are created. Now, with this mold you can create as many patterns in PDMS as much as you want. Okay, do not worry about my this what you call the exact length of the device and all these things. We can make it like this, so that it looks slightly similar to what we are saying. Okay. This is 200 microns, this is also 200 microns. Cool. Alright. So, here we will stop this particular class, and now in the next class we will see the chemical vapor deposition. Chemical vapor deposition, like we have studied physical vapor deposition, and if you kind of recall, in physical vapor deposition at the last section we compared that what are the advantages of physical vapor deposition, what are the advantages of chemical vapor deposition, and what are the limitations of both, right. But one thing that we were sure that in chemical vapor deposition the step coverage is excellent. So, suppose in this mold you have a step of 200 microns, right. If you want to cover this step with let us say silicon dioxide, right, it is easier and it is more uniform, not really easier but more uniform to go for chemical vapor deposition, because the step coverage is excellent. The difficulty with chemical vapor deposition is that the byproduct are the gases. So, you need to really make sure that these gases are not exposed directly to the environment, but are processed through certain technique. So, we will see the types of chemical vapor deposition again, just to understand and not go in depth how the reaction occurs and all these things, but there are different techniques, whether it is APCVD, LPCVD, PECVD, right, ALD, and we will see that one particular CVD which I really like it, which is PECVD. We use it exclusively when it comes to fabricating MEMS based sensors, because the insulating material we have to use it, and that insulating material we cannot grow using thermal oxidation, because if there is a metal which is below this insulating material and the insulating material is grown at 900 to 1100 degrees centigrade, then the metal below it will get affected, will get melt in most of the cases. So, we cannot just keep the wafer where there is already a metal or there is another material below it and you want to grow silicon dioxide. It is not possible, because silicon dioxide growth itself requires silicon, and in that case we go for PECVD. PECVD can be done at way lower temperature, right. So, one of my favorite CVDs, but we will see when we go through that particular class, and then we will take an example as well, followed by we will start going into comparing the different biopotentials, whether it is ECG or EEG or EMG, and then dive into the area of unknown brain, right, and see how we can collect or acquire the signals which are called the neural signals. Okay, so till then you take care, look into the class. I will see you in the next class. Cheers.